Hello students, now we are going to start the chapter atoms. First topic which we have taken, that is the introduction part, then after we will moving on the part alpha particle scattering and Rutherford nuclear model of atom. So let's move with the first topic. Atom. Atom as a whole is electrically neutral and therefore contains equal amount of positive and negative charges. As you can see in this diagram, positive charges are known to be as a proton, which charge is 1.67, which charge is QP 1.6 10 to the power minus 19 coulomb, and the mass of proton is 1.67 10 to the power minus 27 kg. Whereas if I'm talking about the neutron, the charge of a neutron is a neutral and the mass of a neutron is approximately similar as the mass of a neutron, as the mass of a proton. So next, electron. Electron is a very light particle. So the mass of the electron is also light, like the mass of the electron is 9.1 10 to the power minus 31 kg. Whereas the charge of electron is 1.6 in the negative, 1.6 in 10 to the power minus 19 coulomb. The little bit difference between the proton and electron charge. The proton contains positive charge in the nature and electron in negative. As you can see in this diagram, at the central particle, in which neutron and proton are there, that completely positive in nature. What was that? So as in my previous video lecture, I'll just mention this is a nucleus. A nucleus is in positive nature. Reason is because the neutron has a neutral charge and proton have a positive charge. So overall charge of this nucleus is a positive in nature. As you can see, electrons revolving around the nucleus, and the nucleus are in the positive in the nature. They are positively and negatively charged particles. Positively proton, negatively electrons. So positively charged proton inside the nucleus. Now we are moving ahead with this topic, Thomson's models. J.J. Thomson gives the first idea regarding the structure of atom. According to his model, an atom is a solid sphere with the entire positive charge and its mass is uniformly distributed. And in which negative charges, that is electrons, are embedded like a seed in the watermelon. So students, according to the model of Thomson, he proposed that atoms is a form of solid sphere. Students, when we talk about this sphere, this will be as a 3D model. Means they have length, breadth, height also. And the mass is uniformly. So what we have to consider a sphere where the charges are equidistant placed. That means they are uniformly distributed. One over the another charge gap is the same, in which negative charges as an electron are embedded like a seed of the watermelon. So I hope you ever saw the watermelon, where the positive charge all the matters, where seeds are behaving as a electron. So this was the first model, first idea which is gave by the J.J. Thomson. This model is also called as plum pudding model. Now, there are some changements did by the other scientists and said that these theories are not properly corrected. So, J.J. Thomson did some experimental proof for that J.J. Thomson cathode ray tube experiment, in which a vacuum tube he has taken and two charge plate, one is an anode and the other is a cathode plate. They saw that in the cathode plate, the particular light rays are deflecting towards the negative plate. Because of that, they are saying something will be happen over here. So this is a cathode plate which is containing high voltage. This is a gas discharge provide free electrons. Its anode slit, and this is the X-ray deflecting plate. So in the X-ray deflecting plate, as we know that Y-ray or X deflecting plate, these are two plates, evacuated tube we have taken, and fluorescent screen. Means if the charge particle pass from this, a fluorescence, a light, a spark will be generated. Because of that spark, we actually measure that, okay, this is a light which is a false from this fluorescent screen. As you can see the direction, students, direction travel of the cathode ray is this. And this is a light which is a little bit bends towards the Y. So from this complete experiment, what we conclude, we saw in the determination of a specific charge of electron, which is given by J.J. Thomson's method. A narrow beam of a cathode ray coming out from a small hole in the anode moves towards a distant fluorescent screen and produces a bright spot. As we saw in the previous scenario, the narrow beam of a cathode ray coming out from the small hole, which is the plate of anode. Before that, a cathode plate is placed over there. And at the distant apart, at a particular distance, a fluorescent screen. It's an active screen by which if the charge particle continuously collide if this from the fluorescent screen, that particle produces a spark, or we can say after a while it will be converted into a bright spot. The cathode ray beam is made to pass the region where our electric and magnetic fields are perpendicular to each other and perpendicular to the direction of motion of the cathode rays also. If electric and magnetic field are chosen so that cathode ray beam remains undeflected, then force due to magnetic field and force due to the electric field must be equal. The same thing they have taken and created the formula that BEV is equals to E times capital E. B is a magnetic field. E electron, V velocity of the particle, E again, once again electron, and E here electric field. From here we conclude that V is equals to E by B. Here V is the velocity and E is the charge of the cathode ray which is produced by the particle. B is the induction of magnetic field and E is the electric strength as we saw. If V is the potential difference between the cathode and anode through which the cathode ray particles each of mass small m are accelerated, then by work energy theorem we can say VE is equals to or EV is equals to half mv square. Combining both the equation, we get E by m is equals to E square by 2VB square. If the electric field is switched off and only magnetic field is applied, the electron beam will be bent into an arc of a circle of a radius small r. mv square by r is equals to be. E by m is equals to v by br, or E by m is equals to E by rb square. If the magnetic field is switched off and only the electric field is applied, deflection of the electron in the electric field is given by y is equals to half at square. I'll just put this value of a and t. So we get the final equation. E by m is equals to 2ye by L square b square, since v is equals to E by b. So here L is the distance through which the electric field is applied. Success and failures. So J.J. Thomson models successfully explain the phenomena of thermionic emission, photoelectric emission, and ionization. But this model fails to explain the scattering of alpha particle. It could not explain the origin of spectral lines in the spectrum or hydrogen and other atoms. What is the meaning of alpha particle, students? Alpha particle is the positively charged particles which mass is the 4 times the mass of proton and the charge is the 2 times of the charge of proton. Thus, ultimately, this model was discarded. But the first idea which is gave about the atom came from Dr. J.J. Thomson. Now let's move some master's questions. Multiple choice question. The other name of J.J. Thomson's model of atom is Bohr's atomic model, Rutherford's atomic model, de Broglie's model, or a plum pudding model. The correct answer for this question is a plum pudding model. Next, the positive charge of the atom is uniformly distributed throughout the volume of the atom, and the negatively charged electrons are embedded in it like a seeds. In a watermelon is given by Bohr's atomic model, Rutherford's atomic model, de Broglie's atomic model, J.J. Thomson's atomic model, or J.J. Thomson's model. So the correct answer is J.J. Thomson's model. Which of the following could not be explained by J.J. Thomson's cathode ray tube model? So thermionic emission, photoelectric emission, ionization, or a hydrogen spectrum. So J.J. Thomson's cathode ray tube model doesn't explain hydrogen spectrum. Now we are moving with this alpha particle scattering and Rutherford's nuclear model of atom. Moving ahead with the topic alpha particle scattering and Rutherford's nuclear model of an atom. Alpha particle scattering and Rutherford's nuclear model of an atom. Rutherford performed experiment on the scattering of alpha particle by using extremely thin gold foil and made the following observations. As you can see, this is a helium nucleus by which the alpha particles scattered. Here we are placing a collimator by which the beam of alpha particle becomes straight. So this is the source of alpha particle. This is a circular fluorescent paper or a screen, thin gold foil. So the observation is like that when the alpha particle is scattered from the nucleus of a helium, and when it passes from the thin gold foil, most of the alpha particle pass through the foil straight away undeflected. But the thing is that some of them are deflected through the small angle. Question is created from this that how it's possible a reflection particle can pass. Yes, it's possible. Because of that we can say number of vacant places are there, particle are like deviated, so we can say because of the negative charges are there. But the thing is like that only 0.14% of the incident alpha particle is scattered more than 1 degree, and about 8,000 deflection occur. But about 1 in 8,000 deflected by more than 90 degrees. Number of scattered particles in the particular direction are show some different kind of behavior, and this different kind of behavior tells our nature of the nature also. So that n is directly proportional to 1 by sine 4 to the power theta by 2, where theta is the scattering angle. Giger Markston did the same experiment. So who are the Giger and Markston? Giger and Marston are the research scholar of the Rutherford. They are the students of the Rutherford. At the suggested Rutherford, their master actually. So at the suggestion of Ernest Rutherford in 1911, Giger and Marston performed some experiment. In one of their experiment, they shows one figure. Radioactive source from which alpha particle is decaying. As you can see, fluorescent screen also, and non-deflected particles. Well, most of the particles are undeflected because of that vacant places. So they directed a beam of 5.5 mega electron alpha particle emitted from bismuth 83 bismuth 214 radioactive source, a thin metal foil which is made by gold. Alpha particle emitted by 83 bismuth 214 radioactive source were collimated into through lead bricks. The beam was allowed it to fall on a thin foil of a gold of the thickness 2.1 10 to the power minus 7 meter. The scattered alpha particle were observed through a rotable detector consisting of a zinc sulfide screen and microscope. The scattered alpha particle on striking the screen produced brief light flashes or scintillation. What is the meaning of scintillation, students? Scintillation means spark, little bit vibration, different kind of a nature. Like there will be some vibrations occur. So these are the few phenomena which is actually shown by the filament, which is we have taken fluorescent filament. These flashes may be viewed through a microscope, and the distribution of the number of scattered particles may be studied as a function of angle of scattering. This is a complete setup diagram for the Rutherford's experiment, which is performed by their students Giger and Markston. In the Rutherford experiment, they just taken a few steps, whereas further step taken by his lecturer or a formal scientist, which is the Giger and Markston. So symmetric arrangement of a Giger-Markston experiment. A typical graph of the total number of alpha particles scattered at different angle in a given interval of a time. These dots in this figure represent the data point and the solid curve in the theoretical prediction based on the assumption that the target atom has a small, dense, positive charged nucleus. The graph which we occur from this formula, n is directly proportional to the 1 by sine to the power 4 theta by 2. We get this graph where theta is the scattering angle and n is the number of scattered particles detected. Many of the alpha particles pass through a foil. It means that they do not suffer any collision. Only about 0.14% of the incident alpha particles is scattered by more than 1 degree, and about 1 in a thousand, in 8,000 deflected by more than 90 degrees. Rutherford argued that to deflect the alpha particle backward, it must experience a large repulsive force. Students, that we know that repulsive force comes from the two reasons. Either the inside particle have a same nature of a charge as that initial have, or they must have a more power or a more, but the same charges are there. So alpha particle, we know alpha particle's nature is a positive nature. So something which is a hidden inside the core of that atom, which is a nature by positive. This force could be provided if the greater part of the mass of the atom, its positive charge, were concentrated tightly at the center. Why we are focusing about its center? Because most of the alpha particles are deflected by the 90 degree, by the similar way without any deviation, but at the center it's found most, and because of the dot-like pictures we get a very small section of the nucleus where that particular particle is placed. Like in a field, there will be, we have taken a thin of a paper or a simple needle. In a field, in a playground field, nucleus is acting like a needle, which is placed at the center. This argument or this agreement supports the hypothesis of a nuclear atom. So that's why we are saying Rutherford is given a credit to discovery of the nucleus. Why Rutherford? Because earlier which step that is taken by the first, that is the Rutherford, and further study done by in his students scholar, which his name is Gregor Marston. Distance of a closest approach or a nuclear dimension. Now we just want to conclude like what is the nature of the nucleus is actually. It's a spherical in nature, is a triangular in nature, or in the square in nature. For that we need actually how much distance the alpha particle can touch that particular thing. So what is the distance of a closest approach? As we can see this impact parameter diagram, the closest approach we are supposing as a small r. So the minimum distance from the alpha particle of the center up to which alpha particle approaches is called is the distance of a closest approach from the figure. So if you not understood this diagram, students, you can see this. If I'm supposing this is an alpha particle which is continuously colliding here, this is a nucleus which is in positive nature, alpha particle is also positive in nature. So when we just embedded this at a particular distance, after a while it will start to repel. They just not touch together, they just repel at a particular distance. So that minimum distance is called as the distance of a closest approach. This value is r naught is equals to 1 by 4 pi epsilon naught ze square by ke, where epsilon naught is a permittivity of free space. And the value of epsilon naught is 8.85 10 to the power minus 12 Newton Coulomb square per Newton meter square. And K is the kinetic energy. So kinetic energy is equals to half mv square. Now impact parameter diagram. What is the impact parameter diagram? The perpendicular distance of velocity vector v of the alpha particle from the center of the nucleus when it is far away from the nucleus is known as impact parameter. As you can see, students, the light rays are moving in a straight line. After a while, it will bend at a particular angle. That is called trajectory of alpha particle. This is a scattering angle. B is the impact parameter. So B is equals to 1 by 4 pi epsilon naught ze square cot theta by 2 by half mv square. Its derivation is not important for your syllabus. That's why I will not touch that part. So B is directly proportional to cot theta by 2, where z is the atomic number, E charge of electron, theta scattering angle, m mass of the alpha particle, v velocity of the alpha particle. Rutherford's alpha scattering experiment conclusion. What was their observation and what this conclusion based on this topic actually is? That most of the mass and all the positive charges of an atom is concentrated in a very small region which is called as atomic nucleus. Nucleus is a positively charged and its size is in the order of 10 to the power minus 15 meter. 1 Fermi is equal to 10 to the power minus 15 meter. Most of the space in an atom is empty and electrons revolve around the nucleus like a planets revolving around the sun. Drawbacks. What are the drawbacks of Rutherford's model? Stability of atom. It couldn't explain the stability of atom because according to the classical electrodynamics theory, an accelerated charged particle should commonly radiate energy. Thus, an electron moving in a circular path around the nucleus should also radiate energy and thus move into the smaller and smaller orbit of a gradually decreasing radius, and it should ultimately fall into the nucleus. According to this model, the spectrum of an atom must be continuous, whereas practically it is a fine line. It didn't explain the distribution of electron outside the nucleus. Now let's move some questions. The impact parameter is dash distance of the initial velocity, final velocity or velocity of alpha particle from the center of the nucleus. Parallel, equal, unequal, perpendicular. So the correct answer for this question is perpendicular. 1 Fermi is equals to 10 to the power minus 9, 10 to the power minus 11, 10 to the power minus 15 or 10 to the power minus 16 meter. So few seconds before I'll just take in this topic. So 1 Fermi is equals to 10 to the power minus 15 meter. The relation between the distance of a closest approach R0 and kinetic energy of alpha particle is R0 is directly proportional to Ke, R0 is directly proportional to Ke square, R0 is directly proportional to 1 by Ke, and R0 is directly proportional to 1 by Ke square. The correct answer is that R0 is inversely proportional to 1 by Ke or Ke. Fourth question, the relation between impact parameter B and scattering angle. The correct answer is D, P inversely proportional to cot theta by 2. So students, this is all much for today's class. Thank you for watching this video. If you have any doubt, you can ask in the chat session.